Hello, I'm Jung Peck. You're in the computer architecture course. Let's continue our discussion on chapter 5. In this video, we'll talk about encoding and decoding. You've probably heard of these words, encoding and decoding. Maybe when you're listening to music, watching video, and things like that. Okay, you've heard of these words, encoding and decoding. Encoding and decoding is a general concept. Okay, encoding means you're transferring data in one form to another form, usually for some purpose, and then decoding means you're transferring this back, okay, transforming it back to the original form. Encoding and decoding is often used for example, error detection and correction. Okay, you have some data, you encode it, and then you decode it back, and then you want to detect the error or you want to correct error. It's also used for encryption and decryption in security. Okay, this is security. Maybe you want to hide some confidential information, and then later on you want to open it back to see it. Okay, we also use it for compression and decompression. You use compression and decompression maybe practically every day. You use zip, bzip, 7-zip. There are several compression and decompression programs and algorithms that are used every day. Okay, and also for modulation and demodulation. When you do communication, networking, okay, when you want to send some data to another computer or another device, you do modulation, and when you want to receive that data back, you want to do demodulation and so on. Okay, so there are several different kinds of encoding and decoding. And in this lecture, in this course, what we are going to focus on is this one, okay, error detection and correction. Let's look at the picture on the right, okay? Let's say you have this original data. You have this original data, okay? And then you want to encode it. You want to encode it using some encoding algorithm, okay? And the result that you get is the encoded code, okay? Encoded code. You've transformed the original data. Why are we doing this? Well, usually for storage and communication. When you want to store some information in your hard drive, or maybe some disk or flash drive or tape or whatever, backup, whatever, okay? When you want to save it, you want to encode it. Why? And also, when you want to do communication, when you want to send this information to a different computer, communication and networking, you want to encode it. Why? Because when you save some information in the disk, and after some time, you might have some error. You might have dropped your hard disk. You might have, put a magnet near your disk or whatever. I mean, there could be some software bug or maybe some glitch in the power, whatever. Okay, there could be errors. Okay, and we want our store data, or we want our communication to be error resilient. Okay, even if we have some errors, we want to detect that and correct that. So error detection and correction. Okay, for this purpose, we want to encode data. Okay, so later on, you've saved it in the disk, or you want to do communication, and later on, you get that back. Okay, you might read something from the disk, or you might receive some information over the communication. Then we have the received code. Okay, ideally, this and these two should be identical. Okay, ideally. Okay, unfortunately, it's not always like that. I mean, and that's the reason we're doing encoding and decoding. Okay, so what do you do? From this received code, you do the decoding. Okay, you do the decoding using the respective decoding algorithm, and you try to get the original data back. Hopefully, these two should be identical. Okay, ideally. Okay, however, in reality, it's not always like that. Okay, so there might be some error in the storage, or there might be some error in the communication, okay? And if you have some error, okay, we have some error here, okay? Then this will have some error, okay? And this might have some error, okay? So what do? You want to detect that error, okay? Using some error detection algorithm, okay? And if there is an error, okay, we would like to detect it, okay? If we cannot detect it, if we don't know even if there's error, that's bad. Okay, not knowing is the worst. Think about it. Let's say your original data was how much money you have in your bank, and then you get the decoded result, and if that's different, you will not like it. okay? So if there's an error, we want to detect that. This is one reason we want to do encoding and decoding, okay? Even if we don't know what the original thing is, at least we want to detect it. We want to detect whether there's some error or not, okay? Now, what can we do if we have error, okay? If we detect error, okay? One thing that we can do is just drop it, meaning just discard that information, discard that data, forget about it, okay? We may drop the data, that's one thing. At least we know that this data is wrong and we just don't want to use it, okay? Or maybe we can try again, you know, we can retry. Okay, that's another thing we can do, okay? Go to the disk again and get the information again, or maybe, you know, when we're doing communication, you can ask the other side, can you send it again, please? Okay, that's one thing we can do. Or maybe we can correct the error. That would be great, okay? I have this decoded, or I have this received code which has error. I've done the decoding, you get the original data back, you detect error, and you correct that error automatically at the receiver side without retrying, okay? That would be great, right? You get the original data back, okay? So this part is, okay, we say we may try to fix the error, That's error correction, okay? Retry is this, and detect is this, okay? So this is the purpose of doing encoding and decoding. There are variety of encoding and decoding algorithm. We're just going to look at one, okay? Or I can say one or two, okay? Okay, so what we are going to study in this course is something called the Hamming code. Very famous code, very, very, very famous code. So you might want to, you know, remember it, okay? Before explaining what Hamming code is, you want to understand a few concepts. So one of that concept is something called the Hamming distance. Hamming distance is the number of bits that are different between two bit patterns, okay? So for example, if we have this bit pattern and this bit pattern, how many bits are different? This one's different, and this one's different. So we say Hamming distance is 2, okay? Now, why is this important? Let me give you an example, okay? Let's say I have this bunch of students, and your student IDs are random. So let's just write it here. Example, student ID. Okay. So if I look at some student ID, I don't know whether this is a valid, legitimate student ID or not. But let's say, for example, one day, maybe next year, Jungang University says, you know, all student ID must be even number. All student ID must be even number, okay? Then, and there's some bad person say, hey, my student ID is this, and if that number is odd number, you know that there's something wrong, okay? So let's say is even number. Let's say 20191234 is a student number, and 20191236 is student number, 20191238 is student number, and so on, okay? And if someone says, hey, my student ID is 20191235, okay, I can detect error, okay? This is error, right? In this case, we can say the Hamming distance is 2, okay? Because the distance, the difference between the two most closest valid, legitimate number is 2, okay? And if there's anything in the middle, we can detect error. That's the idea. I mean, it's a little bit different. We're talking about binary number here, and then we're talking about decimal number. I mean, that's not important. Get the concept. Okay, get the concept. If we can restrict what numbers are valid and legitimate and what numbers are invalid, then we can detect error. Okay, let's say let's change this. Okay, let's say, for example, student ID is multiple of 3. Okay, let's let's say, you know, Zhejiang University one day announced all student ID must be multiples of 3. Okay, then what can we do? 1, 2, 3, 3 is a student number. 1, 2, 3, 6 is a student number, and 1, 2, 3, 9 is a student number. Okay, let's say these are the valid student numbers. And if someone says, hey, my student ID is 20191234, or if someone says, hey, my student ID is 20191238, I know these are errors. These are all errors. In fact, 20191235 is also an error. Okay? So if I say student ID must be multiples of 3, then my Hamming distance between 3. Hamming distance is the minimum difference between two valid, you know, numbers. Okay? So if I increase the Hamming distance, you can detect more errors. What is the disadvantage? Well, I only have small room for student number. Okay? If I say all student number can be student number, okay? If I say, you know, any number between 0000 to 9999 is a student number, then I have how many possible student numbers? I can have 10,000 students. Okay? But if I say, you know, only even number, then I can only have from 0000 to 9998, and I can only have roughly 5,000 numbers. If I say multiples of 3, then I can have something from 0000 to maybe 9999, but still roughly only 3333 students can be in Zhejiang University, for example. Okay, so if I increase the Hamming distance, okay, I can detect more errors. But the disadvantage is the number of numbers that I can have gets reduced. If I reduce the Hamming distance, the number of numbers I can have will increase, but the error detection will go down. Okay, do you get that? Okay, so I hope you got it. So that's the concept of Hamming distance. Now, if we say the minimum distance, the minimum Hamming distance, minimum distance between the two valid numbers, if that's 2, okay? If that's 2, then it provides a single bit error detection. I can detect 1 bit error, okay? So let's look at one very famous and popular example, which is called that parity code. What is parity code? Parity code is an encoding algorithm. It's an encoding algorithm where you just add one extra bit, okay? So for example, this is 8-bit data, 8-bit data, okay? And this is 9-bit code, okay? This is the encoded code. From the 8-bit data, I've done the encoding, so encoding. Okay, this process is encoding. I've done the encoding, and the code is now 9 bits. What did we do? We added just one extra bit. We just added one extra bit. And what bit do I put? Do I put 0 or 1? Well, very simple algorithm. You just count the number of bits. So, how many ones you have? So how many ones do we have here? 1, 2, 3, 4, 5. That's odd number. So if it's odd, so what we put here, count ones, and then odd 1, even 0. If the number of 1 is even number, we put 0. If the number of ones is odd number, you put 1. Okay. As a side note, of course, you can reverse this. Okay. It just depends on how you design the algorithm, encoding and decoding algorithm. And in this example, let's say I designed my parity code such that if it's even number, I put 1. If it's odd number, I put 1. If it's even number, I put 0. You can design it in a reverse way. That's possible. Okay. But in this example, we've done it this way. Okay. So you've done this, And let's look at the result. Okay, if you look at the result, okay, if you look at the code, oh, sorry. If you look at the 9-bit code, okay, the number of 1 is always even. If you look at the code, the number of 1s must be even, because when the original data had odd number of 1s, we added 1, so it becomes even. If the original data has even number of 1s, we add 0, so the number of 1 is still even. Okay, so the number of 1s in the code is always even. Okay, we make it like this, and then let's say we send this back to this. Okay, we save the code here. Okay, and later you receive the code. Okay, and then you try to decode it. But while doing this, you look at the number of 1s, and if it's even, it's okay. If it's odd, you know that there's an error. Did you get that? That's the idea. Okay? So that's parity code, a very famous, basic, simple, easy, but famous code, still used. Okay? So that's parity code. And I mean, if you want to look at where this is used, if you open up the PuTTY program, when I was showing you some examples on the terminal on Linux machine, I've used a PuTTY software. And if you go to the settings, then you can see this parity code settings. Okay, so parity code is used for serial communication and terminal communication at many places. Okay, so you will probably see this sometime. But anyway, that's parity code. It's a very simple code, easy to understand. Okay, however, it can only detect 1-bit error. If there's 2-bit error, we don't know. Okay, because for example, if we have 2-bit error, let's say we have 2-bit error. Okay, if this became 1 and this became 0, for example, still the number of 1s is even. So you might mistakenly think that, oh, there's no error. Okay, although there was 2-bit errors. So we cannot detect 2-bit errors. Okay, if the minimum distance is 2, cannot detect 2-bit error. And cannot distinguish 2 or more, yeah, 1 or more bit errors. Okay, let me write this more nicely. Cannot. Let me write this more nicely. Okay. Cannot detect 2-bit error. Cannot detect even number bit errors, and cannot distinguish more errors. Okay, so if we have 2-bit error, parity code cannot detect it. Okay, if we have any even number of bits error, then parity code cannot detect it. Okay, and parity code cannot distinguish between 1-bit error and 3-bit error, or 1-bit error and 5-bit error, or 2-bit error and any even bit error. Okay, we don't know. Okay, so the only thing we know, or only thing we can detect is either there's no error or maybe 1-bit error or whatever error. Okay, then hey, is this useful? Well, still it's useful because in today's technology, we're in the 21st century. Okay, memories are good, hard disk is good, communication networking really good. Okay, so even when we have errors, there's not too many errors. Okay, when I send you one information, what is the probability of having no error? What is the probability of having 1-bit error? What is the probability of having 2-bit errors? Okay, that goes down. Okay, so the probability of having many bit errors is probably very, very low. Okay, that's why, you know, just detecting 1 or 2-bit errors is still okay. Okay, it's still useful. Okay. Okay, so that was parity code. Now let's move on to another example when the minimum distance is 3. Okay, we're going to look at a code that has minimum Hamming distance of 3. Okay, the code that we're going to look at is the Hamming ECC code. This is what we're going to study in this video. Okay, and what's good about this is that it can provide a single error correction and 2-bit error detection. That's why we call it SEC and DED code. Okay, what do I mean by single error correction? If there's just 1-bit error and only 1-bit error, I can correct it. Okay? I can fix the error without doing the retry. Okay? I can just look at the code with 1-bit error and I can fix it myself. That's the single error correction capability. And if I have 2-bit error in the code, I can detect it. I can at least know that there is an error, or at least 1 or 2 errors. Okay? I cannot say I can fix it. I mean, I cannot fix it. I cannot fix 2-bit error, but I can at least detect 2-bit error. Same thing, if there's more than 3 errors, or 3-bit or more errors, I cannot distinguish them. Okay? I don't know whether, I cannot distinguish between 1-bit error and 3-bit error, or 2-bit error and 4-bit error. I cannot do that. But I'm just assuming that there's not too many errors. Okay, the probability of having no error, 1-bit error, 2-bit error is, you know, some size, but the probability of having 3-bit error or more error is very, very low. I'm assuming that. Okay. Okay. So let's first look at the Hamming SEC code. So we're going to first look at the SEC code and then evolve into ECC code. Okay, so let's look at Hamming SEC code. Okay, how do we do encoding of Hamming SEC code? Okay, to calculate the Hamming code, we're going to number the bits from 1 on the left, including the data bit D and the parity bit P. Okay, what do I mean by this? Okay, so first of all, okay, let's assume that we have, in this example, data is 8-bit, so 8-bit data. Okay, the data that I want to do encoding is 8 bits. Okay, and I'm going to do encoding. Okay, so, and this is the data bit, so data bit D. So for my 8-bit data, I'm just going to put it here, 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 here. Okay. So what I'm going to do first is create a box. Create a box that looks like this. Okay. Create a box that looks like this. Okay. And I'm just going to put my 8-bit data in this yellow highlighted places. Okay. And then I'm going to say, okay, I'm going to add 4 parity bits. Here, 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 and here. Okay. So first of all, I need to make a table of 12 bits. Okay. 8-bit for data, 4-bit for parity, and this is the order. Order is very, very important. Okay. So I'm going to first create this table. Okay. And then all bit positions that are power of 2 are parity bits. Okay, so what I'm saying is 2 to the 0, 2 to the 1, 2 to the 2, and 2 to the 3 bits are the parity bits. Okay, that's parity 1, this is parity 2, this is parity 4, and this is parity 8. That's the location, that's where I'm going to put the parity bits. Okay, and I'm going to initialize all parity bits to 0. Okay, before doing the computation. Okay, now I'm going to calculate the parity bits. Okay, in the previous page, it was very, very simple. I just count the number of ones in the whole data. Okay, but now instead of looking at the whole data, I'm just going to look at certain bits. Okay, I'm going to check certain data bits marked with X below and calculate the parity bits. Okay, so let's do this. Okay, so if I want to calculate parity 1, I'm just going to look at this bit, this bit, this bit, this bit, this bit, and this bit. So basically every other bit. Okay, I'm going to look at that and then calculate the parity bit. For parity bit 2, I'm going to look at these two, these two, these two bits. And for parity 4, I'm going to look at these 4 and these 4, although this part doesn't exist, okay, bits. And for parity 8, I'm going to look at these 8 bits, although this part doesn't exist, okay. And I'm drawing this extra part. I'm drawing this extra part because although this example is for 8-bit data, I can do this for the 16-bit data or 32-bit data or 64-bit data, okay? So this table can, be bigger if I'm using 16-bit or 32-bit or 64-bit data, okay? This example is just for 8 bits, but I can have a bigger table, okay? So you got the idea and you got the pattern, okay? You got the pattern. So let me delete this part, okay? So what do I mean by this? Let's try. Let's look at an example. Okay, here is our example. Let's say our 1-byte data is this. This is our data. This is our data. So I'm going to put the data at the data bits. So I put 1, 0, 0, 1, 1, 0, 1, 0. This is my data. Okay, data. Okay. And then I'm going to initialize this with the parity bits. Initialize with 0, 0, 0, 0. This is just initializing the parity bits. So this is this part. Okay. Now let's do the calculation. Let's calculate P1. Okay. So I look at this bit, this bit, this bit, this bit, this bit, this bit, and count how many ones we have. How many do we have? 1, 2, 3, 4. I have 4 ones. So parity 1 becomes 0. So this will be 0. Okay. Now let's calculate parity 2. So I need to look at these two, and these two, and these two, and count the number of ones. So that's 1, 2, 3. That's 3 ones. So it's odd number. So this will be 1. Okay. And then let's look again. Let's look at, let's calculate P4. I need to look at these 4, that's 1, and this one, nothing. So there's only 1 1, so that's odd number, so this is 1. And let's calculate parity 8, okay? So let's look at these 5, and then I only have 2 ones, so that's even number, so this must be 0. So that's my parity bits, 4 parity bits. Let's just put that. So I'm going to put 0, 1, 1, 0. Okay. Basically, this is P1, P2, P4, and P8. So that's that. So what is the result? Okay. What is the result? The result is 0, 1, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, which is this. This is the encoded code, encoded 12-bit code. This is the encoded Hamming SSC code. This is how you do the encoding. Got it? I hope you got it. Okay, so let me just repeat the procedure. If I have 8-bit data, I create a table of 12 bits. I put the data at the yellow highlighted places, and I put the parity bits. Parity bits must be at bit positions that are power of 2, okay, numbers. So the first bit, second bit, fourth bit, 8-bit. If we have a bigger table for bigger data, then we will also have it at the 16th bit, okay, and so on. Okay, those are the parity bits. And how we calculate the parity bit, this is the pattern, okay? And you got the idea, every other bit and every other 2 bits for 2 bits, every 4 other bits for the 4 bits, and so on. Okay? Now, we've done the encoding. Let's move on to the decoding. Okay? So how do we decode the Hamming SCC code? Okay. We're going to recalculate the parity bits from the encoded code. We get the encoded code and we are going to recalculate. Okay. We're using the same numbering. We're using the same table. Okay. And the value of parity bits indicate which bits are in error. Okay. I'm going to show you this. Okay. So let's get the code from the previous page. What was the code? Okay. 0111 0010 1010 0111. Let's write it. 0111 0010. Oh, sorry. And 1010 1010. This is the code, right? Encoded 12-bit code. I got it. Okay. Let me recalculate the parity bits. Okay. So I'm just going to count the number of ones. 1, 2, 3, 4. I have 4 ones. So this must be 0. 2, 3, 4. So this is 0. 2, 2. So this is 0. And 2. So this is 0. So when I recalculate the parity code from the code, then this is the parity bits I get. And 0000 means no error. Which is good. Okay. And I mean, it's obvious. We didn't put any error here. Okay. So this is not fun. This is boring. So let's put an error. Okay. Now, let's say our code had an error. Which bit? Any bit you choose. Okay, choose a number. I mean, if I was in class, I would ask some student, maybe you, to choose any number between 1 to 12. Any number between 1 to 12. Okay, and one student would just give me some random number. Let's say 7. Okay, so let's say there's an error in the 7th bit. So let's say this became 0. Okay, let's say this became 0 with an error. This is an error. Let's recalculate the parity bits. Okay, let's recalculate the parity bits. So 1, 2, 3. Okay, 3, that's odd number. So this will be 1. Let's recalculate the parity bits. 2, 3. So this would be 1. And then 1, 1. So this is also 1. And then 2. So this is 0. Okay. So this is the parity bit calculated when we have 1-bit error in 7. Okay. And I told you this is P1, P1, P2, P8, P4, and P8. So let's move this. Yeah, let's move this like this. So we're going to rotate this like this so that P8, P4, P2, and P1 is 0, 1, 1, 1. Right? I'm just rotating it. Okay? Because that's 8, 4, 2, 1. Okay? And binary. So what is this number? What is this number? This is 7. Right? The 7 is this 7. We found which bit had error. Okay? This tells you which bit has error. Okay? And if I know which bit has error, I can just fix it. Fix. Okay? Done. That's what we mean by I can correct error. Where is it? It's not written here, but that's correction. I can correct it. Okay? I can fix the error. I can do error correction. This is how we do it. Okay? You don't believe me? Let's do it one more time. Okay? Let's do it one more time. Okay? So this time it's a little bit messy, so let's go back. Okay? Now, I'm going to ask you again. Ask one student again. Choose any number between 1 and 12. Choose any number between 1 and 12. And let's say, for example, some students said, I don't know, 1. Okay, some students said 1. So let's say we have an error here. Error in the 1 bit. So let's say this became 1. Let's recalculate the parity bits. Okay, so 1, 2, 3, 4, 5. 5, right? So that will be 1. And then 2, 3, 4. So that's 0, even number. And 1, 2, 2, even number, 0. And then 1, 2. So this is 0. Again, we're going to just rotate this. And then what does this become? Okay, 0, 0, 0, 1, right? Binary. And what is this? This is 1 decimal, which tells you that there must be an error. There is an error in bit 1. I found the error. Okay, this is error correction. Okay, I found the error. Then what do? I can just correct it. I can fix this. Fix to 0. And I have the correct data. Okay? So the examples are here. Okay? Let's say if you have the right code, without any error, you calculate the parity bits, and you will obviously get 0, 0, 0, 0. That was this case. Oops. Okay? That was this case. Okay? This case. Okay? 0, 0, 0, 0. And that indicates no error. We have no error. If there is no error, what do? I can just extract the data. Where's the data? Data, 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 data. Okay, that's data. So that I just put it here. Okay, and I have the data, original data, original data. Okay. As an example, let's say there was an error here. Okay, for example, if there was an error here, okay, you recalculate the parity bits, and the parity bits will give you this number, which indicates that bit 10 was flipped. Bit 10 had an error. Okay, so what do? I just fix this. I just fix this to 0. Okay, and then I just read the data. Okay, where's the data? This is data, 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 and data, 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 data. So I can get the original data back. Okay, so what's great about Hamming SEC code? If there's 1-bit error, I can detect it. I know exactly where it is. Okay, it tells you. I can find out where the error is. Okay, and then I can, if I know where the error is, I can just fix it. Okay, get the original data back. Amazing, isn't it? Okay. You might think that, oh, this is magic. Okay, it's not magic. Okay, it's not magic. It's just a well-designed code, encoding scheme, encoding algorithm. Okay, and where is the trick? Where is the trick? Well, it's about protecting the code. Okay, so you have the data, and you encode it. You get the code. Okay, and then you go decode it, and you get the data back. Okay, but when you have this code, you have to protect the bits in the code. Okay, and how is it protected? Well, in this example, so in this very, very simple parity code, we're protecting the whole data using 1 bit. Okay, we're using 1 bit to protect this much data, right? Here, this bit is used to protect this bit. Okay, this bit is used to protect this bit. These 2 bits are used to protect these bits. This bit is used to protect these bits. So this, I mean, 4th bit, this bit, and so on. So if you look at the, maybe I should draw it like this. Okay, and if you look at the pattern. Okay, if you look at the pattern, let me just clear it again. Okay, all of these patterns, they're all different patterns. Okay, they're all different patterns. Okay, so you just look at the 4 parity bits. You just look at the 4 parity bits, look at the pattern or look at the number and know which bit must have some problem, which bit must be flipped, okay? The trick is in the pattern of which parity bit is looking at which code bit, okay? This is the idea. Okay, so I mean, I have this extra page so that you can write on it, but I've already done the examples here, okay? And practically you can try any data and any bit error is gonna solve everything, okay? So practice what I've done. Practice what I've done on this page yourself, okay? Okay, but still, what happens if we have 2-bit errors, okay? If we have 2-bit errors in the Hamming SEC code, what is SEC? Single error correction code, okay? What's gonna happen? The value of parity bits indicates which bits are in error if 1 or less number of bits happen, okay? We were assuming that if it's 0, 0, 0, 0, there's no error. And if there's some number, that bit must be an error, okay? However, if we have more than 2 errors, okay? If I have more errors, we cannot distinguish them, okay? There is no way to distinguish them. So let's look at an example, okay? I mean, okay. So, I mean, I won't write it. You can write it yourself, but let's look at the example at the bottom, okay? Let's look at this. Let's say our code is this, okay? And we had 2-bit errors where we had an error here and we had an error. We had 2-bit errors. Now, if we calculate the Hamming, let's actually do it, okay? 0, so the original should be 0, 1, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0. Let's say this is the correct code, okay? But we had an error here and here, so this became 0, and what is it? This became 0. Okay, let's say we had 2-bit errors. Let's calculate the parity bits. So 1, 2, 3. 1, 1, 2, 1, 1. So 1, 2, 0. So this is the parity bit. You rotate it like this because this is P8 and this is P1. Okay, we get this parity bit, which indicates that bit 5 was flipped. Okay, but no, that's not true. Okay, bit 5 was not flipped. Bit 2 and 7 was flipped. Okay, so we don't know. Okay, we cannot distinguish 2-bit error. If there's 2-bit error, I don't know. All I know is that there's some problem. Okay, why? Because this is not 0. Okay, this is not 0, 0, not 0, 0, 0, 0. If it's 0, 0, 0, 0, 0, then there must be no error. However, if it's not 0, there must be some error, but I don't know whether that's 1-bit error or 2-bit error. I don't know. Okay, so we have a problem. We have a problem. Okay, if you look at another example, okay, just try this. Try this yourself. Okay, and calculate the parity bit. Okay, this will be the parity bit, which indicates that bit 14 was flipped, but there is no bit 14. Okay, there is no 14, right? So still, we have a problem. Okay, so if there's 2-bit or more errors, we cannot, I mean, Hamming SEC code cannot distinguish it, and we don't know what's going on. Okay, and obviously the data that you extract or decode will also be wrong, right? Okay, so if I have 2-bit errors, I have a problem. What can we do? Okay, we can do something. Okay, we can add something here. Okay, so this is the final Hamming ECC code that can do both SEC, single error correction, and also DD, double error detection. Okay, how are we going to improve it? Okay, we're going to add an additional parity bit, one more parity bit called PN for the whole SEC code. SEC code is what we've seen on the previous page, a previous page, okay? We're going to add one extra parity bit to this SEC code, okay? So in our example, because we're assuming 8-bit data, okay, this PN would be P13, okay? We are adding this extra parity bit, okay? And this extra parity bit is calculated for all the bits, okay? Just like the simple basic parity algorithm, okay? That's it. And if I do this, that's going to make the Hamming distance 4, okay? I'm making the distance between two valid data to be 4, okay? Making more room so that I can detect more errors, okay? So, as an example, if we have 1 byte data, this, let's say we have this, okay? Let's put the data 1 0 0 1 1 0 1 0. This is the data, okay? This is the original data, okay? And then I'm going to calculate the parity bits. So let's calculate the parity bits. Let's initialize all of this to 0 0 0 0. Calculate the parity bit. 1 2 3 4, okay? So that's 0. And then 1 2 3, so that would be 1. And then 1, that would be 1. And then 2, this will be 0, okay? So my parity bit would be calculated like this. So the resulting SEC code will be what? This will be 0 and 1, and then my data is 1, and then my parity code is 1 0 0 1, and then 0 1 0 1 0. Okay, this is the SEC code. Okay, and then I'm going to look at this whole SEC code and count the number of ones. 1 2 3 4 5 6. That's even number. So I'm going to add an extra 0 at the end. I'm going to add an extra 0 at the end. So the resulting code would be, I don't have room, okay? But okay, let's just write it here. 0 1 1 1 0 0 1 0 1 0 1 0 0, where this is the extra parity code. Okay, we're just adding this extra bit here for the whole SEC code. Okay, so now if we just look at the parity code, it looks something like this. Okay, where we have this extra P13. Okay, so that's this guy. If you think about the original code, original parity bits, that's this one, this one, this one, and this one. Okay, so once you do this, by adding this extra parity bit Pn, okay, we're making the Hamming distance to 4, and by doing this, we can detect 2-bit errors. Okay. Now, I mean, you can distinguish it. Do I have an example here? Okay, no. Okay, I don't have an example. So let's actually do an example. Let me clear this up. No. Okay. Let me clear this up. 0 1 1 1 0 0 1 0 1 0 1 0 0. This is the Hamming SECDD code. Okay. Now let's say we have an error. Let's say we have 2-bit errors. Okay. If we have 2-bit errors, just choose a number. Okay. If this was a real class, I'm going to ask one student, choose two numbers. Let's say that student chose, I don't know, maybe 4 and 9. Okay. Let's say just 4 and 9. Okay. So let's say 4 and 9. Okay. 4 and 9. So let's say this was 0 and 0. Okay. Now, what we're going to do is calculate the parity bits, but we have to do it in the reverse order of how we've done the encoding, okay? So decoding is the reverse order of encoding. So first, we recalculate this P13. Let's do it. Just look at, count the number of ones. 1, 2, 3, 4. It's even, okay? It's even, so the number of ones is even, so this is correct, okay? So I'm done. I don't have to worry about this. That's done, okay? Finished. Now let's just look at the SEC code. So we're going to just focus on this part now. I'm sorry. Okay, and then calculate the parity bits. Okay, and then calculate the parity bits, and then what are we going to have? 1, 2, 3, right? 3, that's odd, so 1. And then 1, 2, 3, 4, that's 0. And 1, so that's 1. And then, what is it? 1, so that's 1, okay? So let's rotate this. It's 1, 1, 0, 1. And what is this? 12, 13, okay? 13, does that make sense? Does that make sense? Okay? It doesn't. And not just that, okay, 2 things. If this is okay, that means either there's no error or even number of errors, okay? This means no error. So if this is even, it's either no error or even error, okay? Okay? And that does not match with this, okay? So I can tell that there must be 2-bit errors. Okay? Of course, as I've said before, we are assuming number of errors is small, meaning less than or equal to 2. Okay. Earlier, I said, in today's technology, storage communication is pretty good. So the probability of having 3-bit error, 4-bit error is very, very low. Okay. So we are assuming that most likely we have no error or 1-bit error or 2-bit error, just based on probability. Okay. So if we assume that the number of errors is reasonably low, and if we see this and this, we must have just 2-bit errors. We can detect that. Okay, let me just formally list all the cases. So after doing the decoding, okay, you look at 2 things. You look at 2 things. What do you look at? Okay, you look at this, and you look at this. Okay, you look at 2 things. Okay, so this we call H. Okay, that's H. H, the SSD parity bits. Okay. And this is PN, okay? So if H is even, meaning it's all 0, okay? So even means all 0 in this list, okay? And if PN is even, that means no error, okay? All zeros, 0, 0, 0, 0, 0. If H is odd, meaning there's some value in the SEC parity bits, okay? However, and if the PN is also odd, that means there must be odd number of errors, okay? Must be odd number of errors, okay? Odd errors. And if we assume that the number of errors is pretty small with high probability, then we say this must be a correctable single bit error, okay? We have 1-bit error, and we can fix it. If H is even, if H says it's all 0, okay? However, if PN says odd, okay, we must have odd number of errors and probably just 1 error, but H said, the SEC parity bit says 0, okay? So the error must be in the PN bit. So the error is actually here. This bit has the error. Okay, that's this case. This bit has the error. And finally, if the SEC parity code is odd, meaning it indicates some error in the SEC code, but if PN is even, what does this mean? There must be even number of errors, even errors, even number errors. And if we assume that the number of errors is reasonably low with high probability, then we say this must be double error, 2-bit error, 2-bit error, and we've detected it. This is why we call this code SEC-DD code. We can detect, we can correct single-bit error, and we can detect 2-bit error. Okay, and I mean this is also a single-bit error, practically speaking. Okay. Got it? I hope you got it. I hope you got it. Okay, let me clear all of this up. Okay, finally, if you remember what I've said previously, I mean, this was for 8-bit data, 8-bit, so example for 8-bit data translating into 12-bit code, right? What if we have 16-bit data? How many bit code do you think we will have? How many bits of code will we have? Okay. I mean, there must be another parity bit in bit 16, right? P16. And then we can put 13, 14, and 15. I need 5 more. So 17, 18, 19, 20, 21 must be data. So if I have 16-bit data, it must be 21-bit code, right? If I have 32-bit data, what would be the size of the code? Think about it for 10 seconds. I mean, just thinking very simply, okay? At some point, I must have P32, okay? And probably not more than that. So how many parity bits do I have? I have 6 parity bits. And add that to 32-bit. So this must be 38-bit code. Okay? And we can do this forever. We can do this for 64 bits, 128 bits, whatever. Okay? We can extend the same idea. We can extend the same idea for whatever number of data that we have. Okay? This Hamming code is like super good. Now, and if we are doing this SEC-DD code, we have to add 1 extra bit. Okay? So if we add, oh, sorry. So if we do, so this is SEC code. Okay? But if we want to do SEC-DD, SEC-DED code, okay, then we just need to add 1 here. Okay? So that will be 13, 22, 39, and so on. Okay? So this is how you calculate the number of bits you need for the Hamming SEC-DD code. Okay, so if we generalize this, then how many parity bits P are needed to protect D data bits? Okay? Well, if you think about it, we need the parity bits at every power of 2 locations, the bit number that is power of 2, okay? And that must protect the whole code, okay? That must protect the whole code. What is the size of whole code? Whole code is the number of data bits plus the number of parity bits plus 1 extra for the last one, okay? The additional parity bit for the DED code, okay? So this must be bigger than this, right? I must protect all of that. So you just take a log of both sides, and this is how many parity bits we need, okay, to protect the code. Okay? So this is not, I mean, if you look at the equation looks somewhat complicated, but if you just look at, this example, how I've explained it is pretty easy, right? So I've just written it in a very simple way. This is more, professional looking way of putting it, okay? Now, probably all of you, most of you on your computer, you have RAM, okay? ECC RAM. Your RAM has ECC code. ECC, error correcting code, or error correction code DRAM, okay? You have this on your computer, okay? They use this SECDD Hamming code. So that means all of you, including myself, right now are using this Hamming code, okay? You and I both are using this Hamming code right now because we're using a computer right now, okay? You are using this. And in most of the RAMs, until recently, it uses 8 bits or parity bit, 8 bits parity, to protect 64-bit data, okay? Which will give you 72 bits of code, right? 8-bit parity to protect 64-bit data, which gives you 72-bit code. That's why when you go out and try to buy a new RAM, okay, if you buy a new RAM, okay, either DDR2, DDR3, DDR4, you buy a new RAM, if you look at the pin number, it's multiples of 72, okay? Today, I'll just say most, okay? Most RAM you buy today, most RAMs have pin number multiple of 72. If you buy a new RAM, your RAM will probably have the number of pins that are multiple of 72. So it's either 72 pin or 144 pin or 288 pin RAM. Okay, your RAM must have 72, 144, or 288 pins. Why? Because of this. Because of this and this and this. Okay? So now you learn something about your RAM. Okay? Okay, so that's it for today. I will continue in the next video. See you. Bye-bye.